All right, topic 4, lesson 3. So topic 4, lesson 3 is all about heat and materials. So in this whole chapter so far, we've been talking about what heat is. Remember, it's that transfer of energy from one thing to another, the different types of heat transfer. And then finally, in the last section, we're going to be talking about materials and how do different types of materials essentially affect that heat transfer. So guiding questions for the section, how do different materials respond to heat? Another thing that we haven't talked about yet either is how is friction related to thermal energy and temperature? Vocabulary for the section, maybe you guys have seen these words before, maybe not in this context of heat, maybe in electricity, conductor and insulator. Here's a word we've mentioned a little bit before, specific heat, and then finally thermal expansion and then contract. So topic 4, lesson 3, heat and materials. So I want you guys to open your books to page 158, and on 158 we're going to answer the connected question. So for the connected question that we see there, we have a scuba diver, and that scuba diver is underwater, and we're going to assume that the water is cold. So when divers explore deep ocean waters, the temperatures they encounter are very cold. In the space provided, describe how you think the wetsuit keeps the diver warm in cold water. So in that little white box that you guys see on page 159, there is a white box, and there's kind of like a yellow box around it. In that box, you need to go ahead and write, how do you think that wetsuit keeps the diver warm? And then we want to answer the 2 questions that are on page 158. So you also use special clothing to stay warm and perform different functions. What items of clothing do you use for specific activities? So, I mean, think about us in Minnesota with our temperatures and how much they fluctuate. Wintertime, summertime. You can maybe think of a couple of those for examples. And then think about, okay, what materials are these made of? The clothes that you guys use in the wintertime, how are those materials different than maybe the clothes that you guys use in the summertime? So I want you to take some time and then answer that connected question. All right, so if you guys want to pause the video, you can do that if you are not done with this. Otherwise, I'm going to click to the next slide. So if you're not done answering, pause the video. Otherwise, I'm going to click to the next slide. All right, so thermal properties of matter. So remember what we've talked about with thermal energy, right? So thermal energy is that total of all of the kinetic and potential energy of all of those molecules in that matter. A lot of this stuff, the cool thing about this, a lot of this stuff is common sense stuff. So most of us know if we look at the pictures on the bottom of the page there, if I said, hey, you're going to go home and make a casserole tonight, most of you are not going to pick what you guys see on the left-hand side. You're not going to cook in your oven with plastic. You're probably going to pick the pans on the right-hand side, or maybe you guys have glass at home. Whatever the case is, definitely not what's on the left-hand side. Materials respond to heat in different ways. Plastic responds to heat differently than metal does. So the thermal properties of an object determine how it will actually respond to heat. Materials that conduct heat well, we call conductors. So materials that conduct heat well are conductors. So just like we talked about with the oven, if I'm going to cook something. So these would be things like how we said metal pans, or I said maybe you have a glass casserole dish. Another thing that we don't think of often, but this is actually a really good conductor of electricity, is actually the material diamond. So think about any type of a metal we're familiar with. So copper, aluminum, gold, iron, all of those things being metals are really good at conducting heat well. Now on the other hand, materials that do not conduct heat well, we call those materials insulators. So materials that do not conduct heat well are insulators. So those would be things like wood, foam. And when we say foam, think about like styrofoam. So like the styrofoam that we used in the cups in the lab yesterday. Plastic also does not conduct heat well. That's why we're not going to use it to actually cook food in the oven. Now, it's really great that we have both of these types of materials in our world, because sometimes we want materials that conduct heat well, and then sometimes we don't want materials that conduct heat well. If I'm cooking food, I want materials that conduct heat well. If I have hot coffee or hot cocoa and I want it to stay hot longer, I want to put it in something that doesn't conduct heat well so that it's going to stay hot longer. So it's really good that we have these 2 different types of materials for us. Okay, make sure we watch this video. It is very important. Please do not skip through it.
Conductors versus insulators. Conductors, material that allows thermal energy to flow easily through it. Insulators, material that slows down the flow of thermal energy transfer through it. Metals are great conductors and are used as materials for cooking dishes. The particles in the metal move easily to collide with and pass along kinetic energy to neighboring particles. This allows the metal cookware to heat up quickly. Metals quickly transfer the thermal energy from the stove to the food or liquid inside. What do you think will happen if you use a metal spoon to stir your food and you accidentally leave it in there? The spoon will quickly transfer the thermal energy from the hot food to your hand. This could give you a burn. Not only do conductors heat up quickly, they also cool down quickly. Coffee that is poured into a metal cup will cool down faster than coffee poured into a ceramic cup. The thermal energy of the coffee will quickly transfer through the metal cup to the outside air. Paper, wood, and styrofoam are good insulators and are commonly used to keep our food hot or cold and are used as cooking utensils. Ice chests use materials that are good insulators to prevent thermal energy from the outside getting in. This keeps the food inside cool. Coffee containers use materials that are good insulators to prevent the hot coffee from transferring its thermal energy and cooling down. What do you think would happen if you used a wooden spoon to stir your food and accidentally left that in there? The thermal energy from the food would transfer through the wood spoon to your hand, but at a slower rate than the metal spoon. It will feel hot, but not as hot as the metal spoon. You're in charge of designing a new slide at the playground. You can build it out of aluminum or plastic. During your research, you noticed that on hot days when temperatures reach above 40 degrees Celsius, aluminum slides reach temperatures of 32 degrees Celsius, while plastic slides reach temperatures of 34 degrees Celsius. Which slide would you build it out of? Metal is a conductor, so it will quickly transfer its thermal energy over to the person going down the slide. The person will feel most of the heat from the slide. Plastic is more of an insulator. Although it is hotter than the metal, it will not transfer its thermal energy over as easily to the person going down the slide. The plastic will seem less hot to the person. Most playground slides these days are made out of plastic instead of the aluminum of the past. Let's wrap it up. Conductors are materials that allow thermal energy to flow easily through it. Insulators are materials that slow down the flow of thermal energy transfer through it. Conductors heats up and cools down quickly. Insulators heats up and cools down slowly. Example of a conductor would be metal, and an insulator would be styrofoam. Thank you.
Right. So I like that they kind of ended the video there too with talking about how quickly things cool off and how quickly things heat up, because that leads us into our next definition, which is specific heat. And I'm sure maybe some of you guys have noticed this before. Like maybe you've noticed, like let's say when you were little and your parents filled up a kiddie pool with a garden hose, that you couldn't jump in it right away. And if you did, you'd be freezing. That water took a really long time to kind of come to temperature enough so that you didn't freeze. Also think about living up here in Minnesota. Most of us are not going to go jump in the lakes at the end of May, right? Even if the ice is out, even if we've had a few sunny days out, we are not going to jump in that. And that's because water has what we call a high specific heat. So specific heat is the amount of energy required to raise the temperature of 1 kilogram of a material by 1 Kelvin. What it's actually measured in is a joule per kilogram per Kelvin. That's how we say that. Joule per kilogram per Kelvin. So it's all about the materials. So some materials, because of how their molecules are, take much longer to heat up. And then some materials, because of how their molecules are, heat up a lot quicker. The ones that take a longer time to heat up have a high specific heat. Materials with a high specific heat can absorb a lot of energy with a little change in temperature, and that is water. Water can absorb a ton of energy before you can actually get it to change temperature. That's why our lakes take so long to warm up around here, where we can actually swim in them and not freeze to death. In the box there, if a material's temperature changes, you can actually calculate how its energy changes with a formula. So once again, just showing that sort of connection with us for math. So it's important also just to copy that formula in the box down on the bottom, guys, into your notes, because it's going to probably come up in an assignment where you may need it. So energy change, the energy change is equal to the mass of the material, multiply that times the specific heat, and then multiply that times the temperature change.
Hello, and welcome to another ADLC digital lesson. Today, our lesson is on heat capacity. If you've ever been to the beach, you know that the sun can really heat things up. So much so that the sand can get too hot to walk on. But you can always cool your feet off in the nice cold water. But it gets one thinking, why is the water so much colder than the sand when they are both getting heated by the sun equally? And the answer has to do with heat capacity. Sand has a very low heat capacity. Water has a very high heat capacity. That means you have to heat up water an awful lot before the temperature goes up. Sand only has to be heated a small amount before the temperature goes up. So a small amount of heat from the sun can make the sand very hot. The difference between these two substances is huge. You could add tons and tons of heat to water, and it will resist temperature change. You can kind of think of water as having a large trash can for heat. You can put a lot of heat into the trash can before it fills up. Sand would have a very tiny trash can. It can't take much heat at all before the temperature goes up. Again, that is because water has a very high heat capacity and sand has a very low heat capacity. Now we can prove that water has a high heat capacity by doing a simple experiment. Here we have 5 substances: water, wet dirt, dry dirt, wet sand, and dry sand. We're going to compare the heat capacities of these substances by heating each one of them up and recording the temperature. First, we'll start with sand. We do this experiment by putting a temperature probe into sand inside of a pie plate. Then we put the whole thing under a very hot heat lamp for 10 minutes. When that's done, we repeat this with all the different substances. And when we're done, we get a graph that looks like this. Now, if you look very closely, you will see that the graph shows that the water didn't change temperature very much at all. But the dry sand changed temperature quite a bit. It went from 20 degrees all the way up to 54 degrees when being heated for the 10 minutes. Water, on the other hand, only changed temperature a few degrees. Why? Well, remember, water has a very high heat capacity. You can add a lot of heat to water before the temperature will go up. Hello, and welcome.
All right, on page 160 in your book, I'm going to have you guys go to the math toolbox. In the math toolbox, it says a chef is preparing vegetables in 2 pans. The pans are the same mass, but one pan is made of aluminum and the other pan is made of iron. She heats both pans to the same temperature before adding the vegetables. So same vegetables, same size pans, same mass. One is made of iron, one is made of aluminum. Now let's take a look at their specific heat capacities here. So look at water. We've been talking about this, really high specific heat capacity. We can see that. Now look at aluminum. So 900 for specific heat, and then iron is 450. So aluminum has a higher specific heat. So what does that tell us? What have we been talking about? It's going to take longer to heat up, right? All right, I want you guys to go ahead and answer the questions then on page 160. Let me just look through them here quick. All right, I think we should be good based on if we'll watch the video like we're supposed to there. So why don't you pause the video here, go ahead and answer those questions, and then move on and press play to get the rest of the notes. Thermal expansion. So when we heat up matter, so when we're adding energy to it, it'll cause it to expand. So the expansion of matter as it is heated is called thermal expansion. So when we're adding energy to those particles, besides them getting more energy, they're going to spread out. And when they spread out, the matter is going to spread out, right? Same thing. So thermal expansion, particles spread out as they are heated. On the picture there, you guys see on page 161, so if you're in your book on page 161, you can see on the bridge there, they have that sort of like weird area where you see some metal joints there. So bridges actually will have joints that allow for the bridge to expand during the heat. When it gets really hot out, you don't want that metal to be expanding and then it affect the structure of your bridge. So go ahead and answer the question on page 161, and just like normal, pause the video, go ahead and answer the question, and then move on and keep taking notes. Contraction. So contraction, whereas expansion is we're expanding, contraction is obviously the opposite of that. So matter decreases in volume as matter is cooled. So we're taking that energy away, those particles are going to come closer together, and then matter is actually going to contract. So when we make things cooler, they're going to shrink. And the interesting thing about these two words here is the whole reason why roads in Minnesota are absolutely horrible, because we have such temperature fluctuations here, especially in the northern part of the state. When you constantly have this expansion in the summertime, and in the wintertime we have this contraction. We're just sort of setting up an environment for literally what we live in here, and it is not really good roads, because you just can't allow for the things like we do in the bridge there in roads. So this expansion and contraction because of our temperature shifts here really is kind of why we have such bad roads.
Topic: thermal expansion. Why are small gaps left in between rails? Don't know the answer? No worries. We shall find the solution.
So now this video has to do with, in railroad tracks, if you guys have ever noticed before, they are not solid. So it's not one whole continuous rail. There's actually little gaps that are left in those rails.
Did you notice that the level of mercury in the thermometer rose when it was placed in hot water? You must be wondering why this happened, right? It happened because of thermal expansion. Thermal expansion is the tendency of matter to expand on heating. This tendency of expansion can be observed in solids, liquids, as well as gases. Now, let us see how this concept of thermal expansion applies to a thermometer. A thermometer usually consists of a narrow tube with a small bulb at its one end. The bulb and a part of the narrow tube is filled with mercury, which is liquid at room temperature. Now, when a thermometer is placed in hot water, mercury inside it expands due to thermal expansion, and as a result, its level rises. You must be thinking how the gasoline came out of the tank, even though it was exactly filled till the brim. Am I right? Gasoline also expands on heating. So, what happened is that when the tank was filled till the brim, there was no space left in it. Now, when the bike was kept in the sun, the tank became hot, which eventually heated the gasoline filled in it. As a result, the gasoline expanded. But since there was no space left in the tank, expansion forced gasoline to come out of the tank. Do you think that the rails bent because of thermal expansion? If yes, then you are absolutely correct. A railway track is made up of a number of rails joined to each other. These rails are usually made up of steel. Steel expands on heating and contracts on cooling. When the rails are joined to one another without leaving any space for expansion, the rails bend due to thermal expansion and the train goes off the railway track. To avoid this, the rails are not joined together firmly. Instead, each rail is connected to the other in such a way that a small gap is left in between them. These small gaps provide space for easy expansion of the rails, which happens during summer, as well as due to continuous friction between the train wheels and the rails. Hence, these small gaps prevent the rails from bending, preventing any kind of accidents.
So if they didn't put those gaps in the rails, this is going to happen, and then the trains are actually going to go off track, and that would be a very bad thing. All right, so temperature, energy, and friction. Kinetic energy of particles can change as in thermal expansion, but an entire object's kinetic energy can change as well. This change indicates a transfer of energy. So some objects lose kinetic energy due to friction. So for example, if you're riding your bike and you need to come to a stop, the brakes are going to apply pressure to the tire, and as that bike skids to a stop, the tires and the ground are going to become warmer. So you're getting that transfer of energy from your hand to the brakes to the tire, transfer of energy. Not going to be destroying any energy, remember, because of the law of conservation of energy. All right, so on page 162, for the model it in the space provided, draw an example in which friction causes kinetic energy to transfer and transform. So there are so many examples that we can use. They used a bike. Don't use a bike. Let's try to think of something different. But think about when there's two things. Cars would be a great example. So think about cars. If you guys like four-wheelers, any of those sorts of things, think about where is friction on those things and how is there a transfer of energy. So answer model it on page 162. If you want to pause, go ahead and pause. Otherwise, continue on and then come back and do that part. The last thing in the book talks about space shuttles, which is a really kind of sort of interesting side topic. So space is really actually cold. It's really cold. But as space shuttles go out into space, they actually experience really high temperatures due to friction with the atmosphere. They got to get going really, really fast. As they get going really, really fast, as those air molecules are rubbing against the space shuttle, has really high temperatures. So think about if you're building a space shuttle, we have to have materials on a space shuttle that have to be able to withstand really high temperatures as they're moving through Earth's atmosphere. But then once they get into space, they have to be able to withstand really cold temperatures. So it's really kind of interesting how they build space shuttles to sort of have those two sort of ends of the spectrum for temperature. So what type of material, on page 163, there's the reading check on the bottom, what type of material, an insulator or a conductor, should be used to keep an airplane warm inside, and why? So which one do you think? An insulator or a conductor? We want to keep it warm inside, and then go ahead and answer your question why there. I found this really cool sort of infographic here showing us materials for space shuttles, the different types of materials, and then the different temperatures they can withstand. If I just pay attention to the red parts here, those parts of the space shuttle are built with materials that can withstand up to 1,650 degrees Celsius. Think about that. Think about how that thing is moving through the air and why we have in those areas the parts of the space shuttle that are going to be able to withstand those super high temperatures.
Heat is the shuttle's biggest enemy. Built largely out of aluminium, its metal frame simply cannot withstand the temperatures that occur on re-entry.
If the heat from outside the shuttle gets into the structure, it can soften the aluminum so that it begins to fail, melt it entirely, or even set it on fire.
For this reason, the shuttle's designers have developed an elaborate system of heat protection. The bodies of all the craft were covered in white ceramic tiles. These were known to be fragile, but could withstand temperatures of up to 1,200 degrees. The underside of the wing was coated with special dark tiles. These took the brunt of the heat and could face temperatures of 2,300 degrees.
The windward surface of the vehicle sees the next highest temperatures, and these are protected using the black tile that you see here.
But facing the highest temperatures of all were the edges of the wings. They faced temperatures of up to 3,000 degrees. They had been given their own unique protection, called reinforced carbon-carbon panels.
All right, on page 164 then, just a few short questions here. So we have a diagram or a table that's going through different types of materials, showing us some we're familiar with. Oops. Some are familiar with wood, aluminum, steel. Maybe we're not as familiar with this. This is a material called graphite epoxy, and then finally a really cool metal called titanium. And on here, just like many other things that engineers face when they're trying to decide what material should I use, we need to look at advantages and then disadvantages. So all of these materials have advantages, but they have disadvantages. For example, titanium is really strong, it's really lightweight, however, it's very expensive. So you kind of have to take these things into account. So really quickly on page 164, go ahead and answer these questions using the table. Just looking at the advantages and disadvantages of those. And then finally, the last thing that you need to do for Monday is then based on everything that we just took notes on, and in that section, you guys are going to answer the lesson 3 check questions. So 1 through 5, found on page 165. You guys do not need to do the quest check-in, but make sure that you've gone through and done everything else in the book that we talked about.